Okay, so let's continue with isomerism. Okay, this is arguably the most important part of introduction to organic chem. So if you've been dozing off in the earlier parts, you can be forgiven if you study this part well, right? Okay, isomerism basically breaks down into two main types, right? The first type is how the atoms are actually bonded to each other. And the second type is how you actually get the isomer, which are arranged differently when viewed in space. All right. So for stereoisomers, right, which is the one which differs when they view in space, all the atoms, right, are bonded to each other in the same way. It's just that in a 3D viewing, right, they become different isomers. All right. Okay, so basically they have different orientation in space. So that's stereoisomers. Okay, last time the constitutional isomerism, right, it used to be called structural isomerism, but we have since updated it to be called constitutional. All right, for constitutional, there are three main kinds, which is chain, positional, and functional. All right, so for chain is pretty much straightforward. If you have a break in the chain, right, then it is considered a chain isomerism. Like for example, pentane, right, it has 5 carbons joined together in a straight line, all right? And its isomer, right, is structural isomer. The carbon chain is actually broken up so that the longest chain is actually just 3 carbon long. Okay, so the next isomer is a positional isomer. So you have a double bond, right, in the butane between the second and the third carbon, and its positional isomer would have the double bond between the first and the second carbon. Okay. Then when we talk about functional group isomerism, which is the third kind of isomerism, we basically are saying that despite the fact that you have the same atoms, you basically, the way that the atoms are bonded together are different, right? So you actually end up with different functional group. All right, so this functional group here is alcohol, and this here is your ether. All right, so they have very, very different chemical properties. Okay, so that's it for the constitutional isomers. Stereoisomers are actually a bit more challenging to visualize because they differ from each other only in the spatial arrangement, which is what you can see if you view it in the 3D, all right? Okay, so the first isomerism under stereoisomer is Sis Trans Isomerism. What exactly is a Sis Trans Isomerism? All right, so Sis Trans Isomerism, right, only occurs if you have a CC double bond. All right, once you have a CC double bond, and then you have different ways of arranging, right? For example, this example here, right? You have your F atom on the same side of the CC double bond, and for this particular isomer, the trans isomer, the F is on diagonally opposite side. All right, so we call the one on the same side a cis isomer, the one on the opposite side the trans isomer. All right, we need to fulfill certain criteria to exhibit this kind of isomerism, which is number one, to have a CC double bond, because then we can restrict the rotation. All right, we can restrict the rotation, right? And the second criteria is we must have different substituent on each carbon atom. All right, we must have different substituent. Okay, so if let's say it is a single bond, right, you can actually freely rotate it It is actually the same molecule, all right? But when you have a CC double bond, all right, the carbon are actually locked in position, all right, due to the pi bond, all right? So you actually give rise to a stereoisomer, all right, or a cis trans isomer. Okay, so does this two compound have cis trans isomerism? All right, just pause the video for a while and think about it. Do they have cis trans isomerism? Okay, I'm gonna assume that you pause the video, and now let's look at the answer. Okay, so for this compound, no. The CC double bond, right, in a cyclic compound cannot exhibit cis trans isomerism. Okay, for the simple reason, you can't actually get the trans version of the compound, right? You can only exhibit the cis version. If you don't believe me, go ahead and try and draw the trans version. All right, you'll realize what I'm talking about. Okay, so for this compound, no. You realize that your substituents are the same, all right, for each of the carbon, right? Carbon 1 and carbon 2, they have the same substituent, so they don't qualify and won't exhibit cis trans isomerism. Okay, so if you have two double bonds, right, how are you going to label the cis trans isomer? All right, you got to read it from left to right. For example, right, the first CC double bond, all right, you actually have a cis, all right, if you are looking at the two hydrogen. And then the second set of CC double bond, you also have a cis, all right, that's why we call it a cis-cis isomer. All right, so you go the same procedure for the next three isomer, then that will be the way to actually label the cis trans. Please take note to draw the trigonal planar shape around each carbon atom. All right, very simple pair of question, right, that they like to ask, right? Why does the cis isomer have a higher boiling point than the trans? All right, because the cis isomer has net dipole moment, okay, which gives it a stronger PD-PD attraction, and therefore we need more energy to overcome. That's why higher boiling point. Okay, but how about melting point? Then trans has the higher melting point. Why? Because now when we're talking about melting point, right, we're going from solid to liquid. Okay, the trans isomer packs better, right? The trans isomer packs better. They are more compact if you pack them up together compared to the cis isomer. All right, they are less compact in the solid form. All right, so there are more effective IMF and therefore higher amount of energy to overcome. Okay. Okay.